We have a quadrilateral, a cyclic quadrilateral ABCD. And we draw the lines parallel to AC and BD. So let me think about the best way to do this. Let's do it like this. All right, sounds good. All right, so I think EAD is equal to BEC. Oh no, there's some fact about this configuration here that is true. Okay, anyways, so I draw the circumcircled AEB. And EC and ED needed at F and G. Okay, so I'm going to want to rename this point right here. I could call it X. But if let's see. So EC meets it at F and ED meets it at G. We want to show that CDFG is cyclic. So obviously EAXB is a parallelogram. I wonder if we could use the radical axis theorem here. So that's the same as saying A, B, C, D, and F, G concur. And then this would be like a Ricard configuration. Okay, so we could let A, B, and C, D meet at a point. And we could show that that's linear with F and G. It's one way to do it. So yeah, I know there's something about this configuration where you have a parallelogram like this. I think there's some lemma that some angles are equal. Let me check. Is AEB equal to BCE? No. trying to remember, but this looks a lot like an IMO problem. I know there's something about this point that makes a parallelogram with AX and B. And I think there's like some isogonality trick. Let me draw
Maybe we can use EAB is similar to XDC.
EAB is similar to XDC. I think that might be it. Let me but yeah, there's an IMO shortlist problem. I'm not sure if you've seen it before, but I think it has like the same configuration. I don't think it's exactly the same problem, but I think it's a similar idea. I think you construct point E that makes a parallelogram. So yeah, EAB is similar to XDC. So if we extend AB and BC, I think that might be useful. I think that okay, so I think, let me try to draw this.
Is RIE and AG parallel?
I don't think so, because then IG and IE and BF would have to be parallel, right? But maybe those three are collinear.
They have to be from the Sargos, but
From Desargues, they have to be collinear.
so if we can prove they are collinear, it's done. But I don't think it's easy.
Okay.
Maybe Pascal can help, but
That's what I was thinking. So but yeah, I know there was an IMO problem. It said like, it constructs this point E, and then it says, I don't know if it's EID, maybe EID equals XIC. I think that might have been it. Yeah, that's what the IMO problem says. EID is equal to XIC. That's a shortlist problem. And you can prove it using the isogonal line lemma. And it's not that hard, really. So yeah, I don't know if that fact helps. Or maybe it just doesn't help for this problem. But it is interesting, right? Angle EID is equal to angle XIC. And IX is perpendicular to HO by Bricard. Okay, yeah, so it's kind of like we want to use Desargues. Yeah, we want to show I, E, A, G, and B, F are collinear, and then Desargues would solve it. And we know angle DIE is equal to angle BIX. I don't know if that helps. Interesting problem. So let's see, how do we, could we try to use power of a point? So we can try to show EG times EB is EF times EC. That's one way to do it. Yeah, maybe there's another way to use Desargues. Let's see. Are E and X, oh, I was going to ask if they're orthogonal conjugates, but no, I don't think they are. Let me draw that circle. We haven't proven it exists yet, but it did exist. Yeah, let's see what we can do with Pascal. So
Maybe we can try to find the polar of G.
the polar of what?
Polar of G.
Of FG?
Yeah, FG.
So let's see. So HX, if we could find the polar of it and then show H lies on the polar, I guess. So HX is the polar of I. Or, yeah, we could try to show. Okay, so we want to show those are collinear. me draw in some stuff. So I guess another thing we could do is we could try to show that DF and CG concur. Oh, but that's not true. I still like the approach of trying to show IE, AG, and BF are concurrent. Yeah, maybe we could use Pascal's. That's what I'm trying to do. Try this. So what were they? I said angle EIA is equal to angle XIB. Was that really true? Yeah. So yeah, one way we could show they concur is by Desargues. Could we show H lies on the radical axis of those two circles? We need another circle that has the same. I feel like we need another circle through G and F. That might help. Maybe GFX.
It seems CG is perpendicular to ED. Is it correct?
Could be. Yeah. Let me use the measurement. I'm not 100% sure, but I'll check. Oh no, it's not. No, not necessarily. C, D, F, and G. Maybe there's a more simple angle chasing way of doing this. Let's see.
Can you let BD cut the circle? The small one. AJ equals to AX. AB helpful.
Interesting. AJ equals AX.
Just angle chase.
All right. That looks like it could be helpful. So yeah, we would have two isosceles triangles then. AJX and BXK.
Maybe we can do Pascal on these points.
So AGJKBF. So yeah, so I wonder if we want to show those are collinear, but maybe so AG and BF. Yeah, I'm not good at doing Pascal's, but maybe you can help me. So AG and BF meet at a point. Let me write it out on a sheet of paper. That usually makes it easier for me. Hold on 1 second. All right. So AG and BF, and then we want AK.
Actually, AJD is similar to CKB. Maybe this is more helpful.
AJD is similar to CKB. That sounds like it might be useful.
This is angle chase.
Yeah. Is C, let's check if DJKC is cyclic. And I see we have someone new joining, or Furkan Dogmas. So thanks for joining us. All right, so we want to show CDFJ. CDFG is cyclic. All right. So for the person that just joined us, do you want to share where you're from, or are you new, or is it just your name that's showing up on Zoom as new? You can type in the chat too if you want. Let's see. All right, so
He's from Turkey.
he's from Turkey. Yeah, I could see his name looked Turkish.
I shared the link in Telegram.
Thanks for doing that, Serdar. And all right, CDFG. I like the idea of showing FG, AB, and CD are concurrent. But yeah, it's tricky. I wish there was another circle through F and G. So yeah, so you just said triangles AJD and I think it was AJD and BKC are similar. And yeah, it's an easy angle chase. Let's see if that leads to something. Oh, these are hard. These are hard problems. The first couple weren't super hard, but yeah, this one's tricky. Let's see. Is there another way we can use the SAR? It's like,
We can use Brocard in AGFB.
okay. So like let AG and BF meet at a point, and then FG and AB meet at a point, basically. Yeah, maybe what we could do Yeah, we could try using Bricards on that. I'm just thinking
Maybe
about
we can define H as intersection of GF and AB and show H is on DC.
Okay.
Really nice problem.
Yeah, it is a nice problem. So if I want to use Bricards, do you want me to extend AG and BF, or?
I'm not sure.
Okay. Let me draw the center of the other circle. So the other circle is called circle D. So OL is perpendicular to AB. So if CDFG was cyclic, yeah, maybe we could like use the McKell point somewhere, because we know a bunch of circumcircles meet. Like, yeah, I'm just going to draw in a bunch of stuff here. So, for example, like we know that this is like the McKell point of a bunch of. So yeah, that passes through that, which passes through that, which also passes through this. You know, I'm just drawing a bunch of stuff here, but Yeah, like maybe I could, oh, I'm sorry, what?
I am out of ideas, so maybe we can continue.
Maybe, so I have one last idea. So if we let M be the McKell point, maybe we could show IMFG as cyclic. So yeah, I'm gonna first define H. Like if we let M be the McKell point, which is this point right here, we show IMFG as cyclic. Maybe that might work. So yeah, that point lies on a bunch of different circles, obviously. So yeah, it lies on this. But yeah, I don't know how we would show that that's cyclic. Let's see. All right, yeah, I'll move on to the next problem, and we can come back to it in the end. All right, so interesting, we solved 4, and then we have to solve this one, okay. This has an excenter, incenter and an excenter. Okay, so we have the incircled triangle ABC. Oops. And it touches BC at point D. AD intersects the circle at L. So it kind of feels a little bit like poles and polars when we do this kind of stuff. K is the excenter of ABC. So let me do it like this. Actually, with excenters, I like using the incenter excenter lemma. That's kind of my favorite way to do it. So what if I just did this and then I draw this circle, So the other intersection point is the excenter, right? So K, so this is point K. M and N are the midpoints of BC and KM. That's interesting. So first we let this be M, and then we let N be the midpoint of KM. So basically EF is parallel to IM. Maybe this will be straightforward using that fact. It'll be interesting. We want to show that B, C, N, and L are cyclic. Okay, so EN is parallel to IM, which bisects AD by the IM lemma. This is interesting. So yeah, and maybe just for the fun of it, I'll draw this. So DM is equal to MF then, right?
Are NIL concurrent, collinear?
N, I, and L. I think they
Yeah.
are. Let's see, is that? No. That's just, it looked like it, but not necessarily. Yeah, let me see if I can make a better figure, something like that. It still looks like it, but if I make it taller, then it doesn't. There we go. So MI, I mean, I might as well draw the midpoint of AD. MI passes through the midpoint of AD. That's the IM lemma. NI does not pass through L. So I wonder, that circle in the problem through B, C, N, and L, well, that's weird, is, okay, I was wondering if that circle was tangent to the end circle, but I don't think it is, or it's not. So yeah, so what are our options here to show it's cyclic? We could use power of a point. Like what if I reflect N over BC? That's one option. I wonder if that circle has the same size as the circle. Let's see. No, that circle's smaller than the circumcircle BIC. Let me draw it again. So power of a point, that looks a little hard to apply here. Oh, are EN and D collinear? Or is that a no, they're not. Maybe it's worth drawing this point right here because the homothency, or maybe it's, you know what, I'll just draw the X circle just for the heck of it. So that's the X circle. Let me do segments instead. Or, this is tricky. We can try to show BNC is 180 minus BLC. I wonder if BLC is equal to BKC. Let's see. BLC 77.4, BKC. No. So yeah, so IM is parallel to AF, and it passes through this point, which is collinear with I and D. Let me see if I can find another point on that circle. So I have the circle through B, N, C, and L that we're trying to prove. Is there another point on this that I can use? Is this point, so if I draw this, is PN parallel to BC? I think PN is parallel to BC. So basically, okay. So, and then we could use power of a, and that passes through point D. So, okay, so I think that's probably a good strategy. So first, if we let AD, so I think it's a well-known theorem. If AD meets the this circle, oh no, it's not that obvious. But basically, we want to reflect N over the perpendicular bisector of BC, and then AD in that point should be collinear. It's probably an angle chase or spiral similarity or something. But so we would have that. So yeah, let me hide, because yeah, we don't know that this circle exists yet. Let me hide it instead.
Are AD and MK parallel?
AD and MK.
Yeah.
I'm not sure. Let's see. They look parallel. Wait, that's got to be a well-known fact. Well, because MD is equal to MF, so we know that. And can we use that to show they're parallel? If we could show.
You cannot. So you must check.
Oh, actually, I mean, if we define P to be the reflection of N over the perpendicular bisector, because we know DM is equal to MF, it would follow. So once we know that AD and P are collinear, then it would follow that, well, because N is the midpoint. I forgot what N is. So K is the excenter. How did we define N? N
Midpoint of MK.
Midpoint of MK. So yeah, if N is the midpoint of MK, and we define P to be the reflection, we know this is a right angle, right? And we define P to be the reflection of N over the perpendicular bisector, then yeah, if we could show AD and P are collinear, then yeah, it would be true that this is a parallelogram right here. So we want to show ABPC is cyclic. And that I would guess is probably power of a point, right? or I'm sorry, we want to show LBPC is cyclic, which is probably power of a point. Is LD equal to DP? No. So we want to show that, and yeah, dP is equal to mn, which is half of mk. So it's like we want to show LD times mk is twice BD times DC. And that kind of feels like similar triangles a little bit. Draw this. Yeah, there's just a lot of structure here. I feel like it's probably enough to solve. I feel like, yeah. So yeah, we want to show LD times DP is BD times DC. And that kind of feels like a like it would be a trig bash or something. Yeah, how do we find LD? So, I mean, we have triangle OLD, right? And it's a right triangle, and OD is a diameter. So I think OLD is similar to MFK. Let me check that. Yeah. So if we know OLD is similar to MFK, can we use that to show what I just mentioned? So we have OD over LD is MK over FN. Yeah, I think that's like really close. So I don't even know if we. So yeah, I'm just going to start out writing some of this, and then maybe we'll figure it out. So let P be the reflection of N over the perpendicular bisector of BC. We want to show, we still have to show that A, D, and P are collinear. So I'll get to that after I type up some more stuff. So A, D, P, and N are collinear. But we know that BCNP is a cyclic isosceles trapezoid. So So therefore, we could try to show ABPC is cyclic. Or I'm sorry, LBPC is cyclic. And we could show by an angle chase that triangle LOD is similar to FMK. So let me just type out some stuff here. So we have OD over LD is equal to MK over FK, and that means that MK times LV which is the same as 2 PD times LV is equal to OD times FK. Okay. So we would have PD twice PD times LV is equal, which we want to show that's BD times DC, but so OD times FK, that's 2 ID times FK. So basically, I mean, that's the product of the in circles and the X circles, right? So is it like a well-known theorem that ID times FK is BD times DC? I feel like if that's true, it has to be well-known, right? So triangle, I think triangle BID is similar to triangle BFK. Yeah, so yeah, that would prove it. So basically we have triangle BFD is similar to triangle FKB. We'll just say easy angle chase for now. And that means that FK, what does that mean? That means that BI or BD over BD over ID is BF over FK. Yeah.
BFT is not a triangle. I think you miswrite it.
BF over FK. Hold on just a second. So, or what did you say is not a triangle?
BFT.
BF. Oh yeah, BID should be. And that means that wait, is that right? Or, that might be FK over BF. I think it's FK over BF. Yeah. So that means that BD times DC is equal to FK times ID, which from this is equal to okay, so if you combine these two, then you get that PD times LD is BD times BC. So that means it's cyclic. So or just to make it even clearer, I'll say this. Okay, so we still have to show that claim that I mentioned earlier. And maybe write out a little more detail of this proof. I think this is the idea. Whoops.
Did we use that LOD is similar to MFK?
I used it in this ratio right here. Yeah, I used it in this ratio right here. So LOD is similar to MFK. So I'll write it right here. The fact that those are similar makes this ratio right here. So then we get all these equality.
It's just left that we have to prove AD is parallel to MK. Then it's obvious that LOD is similar to MFK. And ADP are collinear. So we have to prove that AD is parallel to MK.
Okay, so we have to show AD is so it's obvious once we show that AD is parallel to MK, it's obvious that AD and P are collinear.
Yeah.
Okay. All right. What was N again? I forgot. N is the midpoint of the KM. That's right. So we know IM is parallel.
I found the proof.
Okay.
We have to name contact triangle.
Okay.
Now observe that DL is median of QDR and KM is the median of the triangle formed by excenters. And because they're homothetic, they must be parallel.
Okay, hold on one sec.
Can you name other X circles, excenters?
Yeah. I'm just thinking of the fastest way to do this. So I don't think it has to be that. I think it's really just an angle change. We just want to show AD is parallel to KM, right?
Yeah.
Maybe it is that hard. I don't feel like it should. You're saying to draw the other two excenters. Let me first see if I can find like another way. So I guess I would be a little surprised if it were that, if there weren't an easier way.
Actually, I think there is another way. I'm not sure.
Okay.
I saw a similar problem, similar configuration.
Yeah.
And I proved it differently from the proposed solution. So there can be another proof, but it seems rather long. Not complicated, but long.
But a little bit long. Okay. Okay, we want to show Km is parallel to AB.
I found the other way, but it's not so easy. It's if you reflect K over M, you will find the orthocenter of BIC.
Okay.
Then we will have to prove that MH is parallel to AD. Then we will let intersect BC. Then we will draw the perpendicular from A to BC. Then we will have to show just similarity. Then
Wow.
chase.
Okay. Yeah, maybe the excenter way is the best way. Let's see. The similarity equation must be BD over ID is FK over KB. Or I think FK over BF, right? Or, well, because KB is a hypotenuse. Or maybe,
No, that's right. Equation is right.
what for Conroad or what's written here?
There's nothing wrong.
Okay. All right. So, yeah, let me just think for like 5 minutes of another way, if I can think of another way to show AD and MK are parallel. Oh, it's all right. No worries. Yeah, I'll just think about it for 5 minutes, and if I can't figure it out, then I'll write it up the way you mentioned. So yeah, I think, what if we draw the midpoint of AF? Then MS, so if S is the midpoint of AF, then MS is parallel to AD. So we want to show that S, M, and K are collinear, basically. I kind of like that idea. And then, yeah, so I think, so basically that means if we draw this line, so AD, okay, so yeah, so by homothety, I think AD and FK concur. Yeah, so I think it's it's fairly simple, because yeah, basically by AF and AD and FK meet on the AX circle, because a homothety takes AOD to AFX, let's say, and so since M is the midpoint of FD and K is the midpoint of FX, then MK is parallel to AD. So yeah, I think that's a fairly simple proof of it. Okay, so I'll move all this stuff down and make room for that. close. Okay, so by a homotopy at A, AD and FK meet at a point X not shown that lies on the AX circle. Maybe I can make room for point X. Let's see. I'd have to maybe shrink stuff a little bit. Move stuff around just a little bit. There we go. So, okay, so that would be point X down there. We're going to show this, so I can delete that. Let me just make a little more room here. Okay. So basically, we can call this point X down here. And then K is the midpoint of Fx and M is the midpoint of FD. So MK is parallel to AD. Hey, Akan. So now we have 3 people from Turkey. All right. So we have about a half hour left here. So K is, I'll just say Fk equals Kx and Fm equals Md. So that means that Km is parallel to AD. All right. And once we know that,
now actually, if we let NP be aligned parallel to BC, then we can show that DM NP is parallelogram.
Okay. And then how would we show that A, D, and P are collinear? Is that obvious?
DM equals to MF and equals to PN. So midpoint of PN is on the perpendicular bisector of BC.
Okay, so you're defining P to be, let P be the intersection of the parallel to BC with AX, is what you're saying?
Yeah.
Okay.
Okay, I found it. It is just to prove now Fn equals to dP. After that, we have to prove Fn equals to dP, and this is from
that's obvious.
Mn equals to dP.
Okay, so P is the intersection of the parallel to BC with AX. And so, yeah, obviously AD, P, and X are collinear. But it's, I guess by symmetry, it's obvious that BP and C is an isosceles trapezoid. So, well, wait.
Actually, it's not obvious, but we can prove that dP equals to Fn.
dP
After
is equal to
that,
Fn. Okay, after that, it's obvious.
Yeah.
So
how
do
we will use Fn equals to Mn because it's right triangle and N is the midpoint of MK.
Okay. So Fn is equal to Nm, and Fn is equal to dp, since it's a parallelogram. So that basically means bpnc is okay. So yeah, from there, yeah. So I think this is pretty much a complete proof.
Can you change Fk to Fn?
Yeah, sorry.
Really nice proof.
Yeah, I like it. Maybe I could just like add in a little bit more of an angle chase here to show that LOD is similar to MFK. Whoops. Sorry about that. All right. So let's see. So angle, I mean, yeah, because angle LDO is equal to angle DXF by the homoptity, which is equal to, what do I want to show? Angle MFK is equal to angle MKF. Yeah. That proves this similarity. Yeah, I think that's everything. Just thinking. All right, so I will move back to some of our previous problems, but I think, yeah, I mean this angle chase here is easy because angle IBD plus KBF, like angle IBK is 90. So I'll just leave that to the viewer if they haven't seen that before. All right, so we did. So yeah, maybe Hakan can help us out with which problem do you want to do? Do you want to do this one or do you want to go back to this one? So yeah, we haven't solved these two. Which do you prefer?
This seems easier. This seems easier. We must do this.
This one?
Yeah, this one.
Okay. All right. 1 second. I'll be right back. All right. So yeah, we have to use that PI is equal to PD. That's what we had trouble doing before. Can I extend AJ to meet ABC? Yes. Yeah, I tried that before. So yeah, basically we want to show that GQ is parallel to BC.
He said BC actually.
Oh, really? Okay. My bad.
No, I misread. It's ABC.
Oh, oops. All right. So yeah, one thing Serdar was saying earlier is if we could show AJF is similar to ACQ, that would solve the problem. You know what? Maybe it is worth extending it to meet BC, because then we could try to show that AHEP is cyclic. Yeah. Whoops, why does it keep doing that? There we go. Yeah, there's the real question is, yeah.
We prove that it's just angle chasing.
Yeah, if we can prove that AHEP is cyclic, then it's just angle chasing. Maybe we could try to use, like, what if I draw a perpendicular here? Yeah, because the perpendicular at I, it's tangent to this circle. Let me let it meet BC at another point. So, because, yeah, I'm trying to use that PI is equal to PD. So I see someone wrote something in the chat. Give me just a second.
Yeah, it's cyclic.
Come on. Is, oh, ADPQ. Yeah, yeah, P is defined, or I'm sorry, Q is defined so that APDQ is cyclic.
It is easy to show that AD and PQ intersect on ABC, circumcircle of ABC. We proved that earlier.
Yeah. All right, so yeah, so IK is tangent to this circle, and PI equals PD equals PK. I don't know if that helps. Maybe it doesn't. Can we compute IJ somehow? That would be interesting. Yeah, because like IJ, like if we let this point, if we draw point L right here, IJ, it's BC minus 2CL, right? So that kind of gives us a way to compute it. We could get AI over AD equals IJ over HD. Okay. And then power of a point can work. So how would power of a point work to show that? HD times DP is AD. Oh, you do want to use the point H. Okay. Or that's an idea. I kind of like that. Let me write this out a little bit. So, yeah, because IJ, that's like BC minus 2CL. That's a little bit tricky. Well, maybe not. Because BC minus 2CL, that's just, yeah. Is BJ parallel to?
Oh, it's not actually.
Yeah, I don't think BJ is parallel to AE. No, but still, we know BJIP is an isosceles trapezoid. So yeah, IJ is BC minus 2CL. So basically, if we draw the external tangency point here, so like let's say, so if I reflect D over point M, so D prime is where the X circle touches BC, right? Wait, no, that's not right. I want to reflect L over point M. So so L prime is where the X circle touches. So L prime, that's the distance between the tangency point and the external tangency point, right? So IJ over HD is LL prime over HD. So let me write this out. LL prime over HD. And that is equal to AI over AE. Okay, so we want HD times DP. So HD times DP, I'm just writing this out. That's LL prime times AE times DP over AI. And we want to show that that's equal to AD times BE. So DP, oh, but yeah, we have to compute DP, and I feel like, well, DP is the same as IP, but yeah. Yeah, I think that's right. I think IJ is C minus B. Well, I think that's right. But the problem is when we use power of a point, how do we find DP? That seems a little tricky to me. Yeah, I don't see a good way to calculate DP. That's the thing. Maybe it can be done with similar triangles. I'm not sure, but it doesn't look that easy to me.
Can you name the intersection of the perpendicular bisector of BC and IJ?
BC and IJ. Yes. One second. Here's the perpendicular bisector.
No, BC, yeah.
There we go.
PN is, no, it's not.
Is there any stuff we could do with the medians? Let's see.
Can you let BI cut NM?
Yes. I don't think they intersect on us. There we go.
An intersection point. PO is parallel to KI.
PO is parallel to KI.
Oh, it's not.
No.
You can delete these. It's useless.
This is hard. Wow. Yeah, we have to use PI equals PB. That's the key. I think so often. So that means those two. So let me see. Yeah, this is a tricky one. Do you want to go back to the other problem, or do you want to stick with this?
I think we can do this.
All right, let's do it. Let's see. All right, BAQ. So yeah, this looks good. This, yeah, maybe the X circle helps here. Um, I don't know if it's worth actually drawing the X circle, but I'm just keeping it in my mind. It looks like AJ is tangent, but I don't think it is. No.
We have to prove that IJ equals to ED multiplied by AC over CD.
Say that one more time. IJ is equal to
ED multiplied by AC over CD.
Are you sure it's that would solve the problem?
Yeah.
Because IJ is pretty computable. Yeah, that if that's it, it doesn't seem like it would be that hard. So because IJ is the same as LL prime, right? And ED times AC over CD. So CD is just where the angle bisect. I mean, AC over CD is AE over BE. So okay, so yeah, because triangle ACD is similar to ADB. So AC over C, I'm sorry, ACD is similar to AEB. So AC over CD is AE over EB, and EB is that radius. So that would be ED times, so it would be ED times AE over BE. So wait, I think that comes to just I don't think that statement that you just said is right. Because yeah, ED times AE is BE squared. So I think what you just said would simplify to IJ is equal to BE, which I would be very surprised if that were true. But yeah, but how did you get there? Like how did you get to that? What made you think that that would solve it?
I wrote similarity, but I will try to write it again. Wait a minute.
Okay. So was it because you were trying to show AFJ is similar to AQC? Is that how you got that?
I am trying to prove that HD multiplied by DI equals to ED multiplied by DA. Oh, sorry. That's where I'm wrong.
Oh, you found a mistake.
Yeah.
Interesting. That is a good problem. All right, so it's already 1 p.m., so I think I'm going to stop here. So thank you both for your participation. This was a lot of fun. So for everyone watching, if you like my videos, subscribe to my channel. And if you want to join future sessions, you can email me at mgreend801@gmail.com. We meet on Sundays at 10 a.m. U.S. Central Time. So thanks for watching.